Hi everybody, this is Mr. Short. Today we're going to be learning about complete electron configuration. But I want you to start by using your background knowledge of atomic structure to see if you can fill in the blanks right over here in these two paragraphs. So hit pause and see if you can fill those in. Alright, now I've already got this filled in. We'll go through and we'll read this and make sure we understand why these are the correct answers. So just to start with, I had written this in with a class a couple of years ago, so you'll see some things that students told me to write down that we later crossed out. So here's how it should read. We recently learned that atoms are electrically neutral, which means that they have an equal number of protons and electrons. So let's think about that. Atoms are electrically neutral. That means they have no charge. The reason that they have no charge is because they've got an equal number of positively charged protons balanced out with negatively charged electrons. Additionally, we know that an element's atomic number equals its number of protons, and that ions are formed by a gain or loss of electrons, never protons. Okay, so if you see a charge on something, the only way that that charge is formed is by gaining or losing electrons, never protons. Here's what's new though. In this section, we will focus on describing the location and behavior of electrons in atoms and ions. And the first level of description is called electron configuration. Now I want you to know that the word configuration just means arrangement. So the way that we're going to learn this at the beginning is by describing the arrangement of electrons inside atoms. The way that we describe the arrangement of electrons inside atoms is by using a technique that looks like this down here. So I think that you were introduced in this technique with a recent ed puzzle. Let's start with the guiding questions over on the left-hand side. What is the order of electron configuration? Here's the order. You can see I've got it highlighted. It's not something that you need to memorize. I'm always going to give you this, but you need to know what to do with it. What are examples of electron configuration, complete electron configuration? What do they look like? Okay, so let's stop and think about this. Up here, we learned that because atoms are neutral, they must have an equal number of protons and electrons. So here, because we're talking about neutral beryllium, there's no charge, beryllium must have not only 4 protons.
Dylan Woodruff, would you please copy?
Sorry, there's an announcement over the loudspeaker.
Dylan Woodruff, would you please copy student services?
Must have not only 4 protons, but also 4 electrons. We want to represent those 4 electrons in this complete electron configuration. So we always start with this pattern by reading left to right. So we always have to start with 1s, and we're going to write 1s2. And then remaining electrons spill over into the second energy level and sublevel, so we're going to use 2s2. And you can see that the sum of these exponents, 2 plus 2, adds up to the 4 electrons that we want to represent for beryllium. So we would say that beryllium's electron configuration is 1s2, 2s2. For neon, neutral neon has not only 10 protons, but also 10 electrons. Its complete electron configuration would be 1s2, 2s2, 2p6. Because notice that 2p comes after 2s. So I think you guys are starting to see that you have to follow this pattern, you have to follow this order of electron configuration. Here's germanium. Germanium is a little bit bigger, and so we're going to have to write a bigger electron configuration for this. Neutral germanium, would have 32 protons and therefore 32 electrons. Its complete electron configuration would be 1s2, 2s2, 2p6, then 3s2, 3p6, then 4s2, then you can see after 4s does in fact come 3d. That's not a typo. So after 4s2 it goes 3d10, and then the next after 3p is going to be 4p. It's going to be 4p2. And if we add up the sum of these exponents, you're going to see that the sum of the exponents adds up to 32. And a really simple way to figure this out when you've got a long electron configuration is to chunk up the information here, here, and here. This chunk of exponents is 10, plus another chunk of 10, plus 10, so that all adds up to 30, 32. 32 electrons are written right there. Okay, now again in the ed puzzle this was introduced to you. each sublevel can hold a maximum number of electrons. So I like to think of these sublevels as if they're buckets. Buckets have a maximum capacity, maybe for water that they can hold. And likewise, each sublevel has a maximum capacity for the number of electrons that it can hold. S is a sublevel that can hold 2 electrons. P is a sublevel that can hold 6 electrons. D is a sublevel that can hold 10 electrons. And F is a sublevel that can hold 14 electrons. Now again, in the Edpuzzle, we took a look at this and we said, just like the S sublevel holds 2 electrons, there are also 2 vertical columns in the S block of the periodic table. P holds 6 electrons, and there are 1, 2, 3, 4, 5, 6 vertical columns in the P block. D holds 10 electrons, and from left to right here in the D block, there are 10 vertical columns. F sublevel holds 14 electrons, 14 vertical columns from here to over here. So again, it goes S, P, D, F. Okay, and those numbers are 2, 6, 10, and 14. If you ever forget the maximum capacity, just remember it starts with 2, and then it's a series or a sequence. You keep adding 4. So 2 plus 4 is 6, plus 4 is 10, plus 4 is 14. Okay, so I want you to notice that information comes in chunks of 3 in electron configuration. So consider this. Here's a chunk of 3 that we've got in blue right here. 1s2 is a chunk of 3 pieces of information. Likewise, 3d10 is a chunk of 3 pieces of information. Let's break this down and make sure that we understand what each chunk within the chunk of 3, what each piece of information means. The number that's out front, the 1 or the 3, is called the energy level. And this is like a ring in a Bohr atomic model. We'll take a look at that in just a minute, and I'm sure that you were introduced to Bohr atomic models in 9th grade. The S, or in this case the D, is called a sublevel. Remember, the sublevels are S, P, D, and F, which are like buckets that can hold a maximum number of electrons. And then the exponents are the electrons themselves. So this 10 right here means 10 electrons in a D sublevel, excuse me, in a third energy level. This here means 2 electrons in an S sublevel, and that S sublevel is on the first energy level. Okay, so you can see down below what we're going to do is we're going to take a look at the electron configuration for neon and for germanium. We've already got those written right up here, but I've rewritten them down below. This is how you take a look at an electron configuration and turn it into a Bohr atomic model, here or here. Okay, so what you do is you write the complete electron configuration, and then you read it and you follow it as a series of directions. What I would do is I would say, okay, 2 electrons on the first ring, the first energy level. So you can see first ring, 1, 2 dots, 2 electrons. 2 dots on the second ring, 2 dots on the second energy level. So maybe it's this dot and this dot. But then also on the second ring, another 6 dots. Well, that means 6 plus 2 dots, that's going to be 8 dots on the second energy level. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, the reason I've got these underlined is as I'm doing this, I underline it so that I don't accidentally do it twice or forget to do it. Over here, 2 dots on the first energy level, 2 dots plus 6 dots on the second energy level. You can see that's a total of 8 dots right here. Third energy level is going to get crowded. I would do it like this. 2 dots on the third energy level, plus another 6 dots on the third energy level, and I would put those 8 dots in there. Then I would go up and I would draw the fourth energy level, and I would draw 2 dots on the fourth energy level. 1, 2. Then I would drop back down to the third energy level, and I would draw another 10 dots. Well, if we do some accounting here, that's 2 on the third, plus 6 on the third, plus 10 on the third, 18 total dots on the third ring on the third energy level. Then I would go back up to the fourth energy level, and I would draw 2 more dots on the fourth energy level. Well, we already had the 2 there, so this is maybe this one and this one. That's a total of these 2 plus those 2. That's 4 dots. 4 dots on the fourth energy level. Okay, just a couple of notes about this. Just note that sublevels don't actually appear in Bohr atomic models. The only thing that we see in Bohr atomic models are the rings, which are technically called energy levels, and we also see the dots, which are electrons. So we do not see sublevels in the Bohr atomic models. The other thing is, I want you to know that you're not actually going to have to draw Bohr atomic models in this class. Bohr atomic models are a nice model for us because it lets us visualize where the electrons are at and how many are on each ring, but it's not actually the way that the electrons appear inside an atom. Okay, we're going to learn a little bit more about the wave mechanical model of the atom coming up in the future. So just understand that you're not going to have to know how to draw these things, although they can be nice visualizations if you do want to draw them. All right, thanks a lot, guys. Again, that is a lesson on complete electron configuration.